So let's go over some more electron configurations. And I know we spent some decent time last week working on some electron configurations, but we're going to continue it. What is the electron configuration for carbon? Sorry, that is C, then calcium, then sulfur, and then iodine. Okay? We're going to work out these 4 electron configurations, and as we do, continue to highlight some of the points that we made last week, but then we're going to take it to the next step and say, so what? What information can we gather from these electron configurations? So first framing question is, what is the electron configuration for carbon, calcium, sulfur, iodine? You probably already have this question written in your notes, and you can just continue your list. So last week we used this periodic table in addition to your own periodic table to get an idea of what our electron configuration should look like. All right, so let's do this for carbon. If you look at your periodic table, carbon sits in this position here, correct? So the electron configuration for carbon should end in 2p, right? And specifically, it should end in 2p2, and we'll get there in just a minute, but we know that the electron configuration for carbon should end in 2p because carbon is positioned in this 2p subgroup. Yes? But we know from last week that in order to start putting electrons into this subgroup, we need to fill every group that's a lower energy. Okay? And so where do we start? What's the lowest energy orbital? Yeah, Joe. 1s. And if we're going to get to 2p, we better have completely filled 1s. And how many electrons can 1s hold?
2.
2 electrons. It is an s subshell. S subshells have 1 orbital, and 1 orbital can hold 2 electrons. Okay, what comes next? Yeah, Tom? 2s. And this will also be 2 because in order to start putting electrons in here, we have to completely fill this. This is an s subshell, has 1 orbital, and 1 orbital holds how many electrons? 2. And so now we have accounted for 4 electrons. If you look in the upper right-hand corner of the symbol on your periodic table, it tells us how many protons carbon has, which is also the number of electrons carbon has if it's neutral. And what is that number for carbon? 6. So we've accounted for 4 electrons. How many are in this subshell then? 2. Be careful calling this an orbital, because this is not an orbital, this is a subshell. These 2 subshells happen to only have 1 orbital, but this subshell has how many orbitals? 3, right? Cool. All right. So that is the electron configuration for carbon. Josh.
In the book, when we were reading over it spread the electrons over the different parts.
Different parts of P?
Yeah.
We'll talk about that in just a minute, because some people don't like having 6 here and instead split it into the 3 orbitals, which you're certainly welcome to do if you want to do that.
They had 3 electrons and they had 1 in each instead of 2 in the first.
Right. And that's what's typically going to happen is you would fill. So if you have, that's what is going to happen if we amplify this out. There are 3 different orbitals. There's 2px, there's 2py, and there's 2pz. And they're all the same energy level. Okay? It's not like 2s compared to 2p. 2s is a lower energy level than 2p. But all 3 of these are the same energy level. So now we have a question of, okay, we know that electrons go into that they fill the lower energy levels before they can go to a higher. But what happens if we have multiple orbitals that are all the same energy? And what happens in those cases is that the electrons remain unpaired as long as possible. And so that's why you would put 1 here, and one here, and you wouldn't fill the 2px before you went to the 2py. Yeah, but we'll talk about that in a minute. Yeah. Okay. So this is our electron configuration. We have 2 electrons in our 2p subshell because we had 2 electrons remaining after we filled these subshells. But we could also go back, and last week we talked about, is it a coincidence that we have these s subshells hold 2 electrons, because they have 1 orbital, they hold 2 electrons, and there happen to be 2 elements in each of these. Is that a coincidence? So we have 2 elements here. So if you look at your periodic table, let's do the 4s. Your periodic table, we've got what, potassium and calcium in these 2 positions. Okay? And we know an s subshell holds 2 electrons. Is that a coincidence? So we have 2 elements and we have 2 electrons. And we would suggest probably not, and to confirm that, we would say, does it hold up for the rest of these? How many elements are in the 2p subshell? There are 6. And how many electrons fit in a p subshell? 6. How many elements are there in this 3d subshell? 10. And how many electrons fit in a d subshell? 10. 5 orbitals, 2 electrons each. Same thing with the F. There are 14 elements here, and how many electrons fit in an F subshell? 14. It is not a coincidence. The periodic table is structured this way to accommodate that. And so another key or another piece that we have to check our work is to see if it makes sense position-wise. So this would be the first element in the 4s subshell. Would you agree? So the electron configuration of potassium should end in 4s1. Look at your periodic table and look at potassium and look underneath it where it gives you the electron configuration. Does it end in 4s1? Yeah. It does. And does calcium end in 4s2? Yep. Coincidence? I don't think so, but let's check just to make sure. So then we look at, this should be boron, right? On your periodic table. And according to this, it should end in 2p1. Does it end in 2p1? Yeah. It sure does. This should be carbon, and we already know that that ends in 2p2 because we just did it. And then here is nitrogen, and that should end in 2p3. Does it? Yeah. You bet it does. And here's oxygen. That should end in 2p4. Does it? Yeah. Oh, yeah. And this is fluorine, and it should end in 2p5. Does it? Yeah. Yes. And this is, let's see, don't tell me. It's not argon. Is it neon? Yes. And neon should end in 2p6, does it? Yeah. It does. So here's 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And here's 3p1, is it? Yep. Here's 3p5, is it? Yes. Here's 4p4. Does that one's electron configuration? Let's see, this should be oxygen, sulfur. Ooh, is this selenium? Yeah. Okay, so selenium, does it end in 4p4? Yeah. It sure does. Coincidence? Certainly doesn't look like it is a coincidence now. So now we have 2 ways we can check our answers. Well, actually we have a third, which is to look at your periodic table, but that's lame. We have 2 ways to check it. One, are they in the position to where it ends in the right number, and does it account for all of the electrons? We've got 2 ways to check it. It's wonderful. Wonderful news. Because when we were doing our stoichiometry, there's only one way to check your answers for those. Look at the answer. Does it match? Right? Here we have 2 ways to check our answer. That you don't even have to check an answer. You can be confident because it's accounted for all of the electrons and it ends in a reasonable number. Alright? Cool. Let's do this for calcium. So calcium is sitting right here. So according to this, it should end in 4s2. Right? And we already know if you look at the periodic table, it does end in 4s2. But the periodic table, your periodic table only gives you a shortened version of the electron configuration. It doesn't give you the entire electron configuration. Let's do it. Okay? So we know if we're going to start putting electrons into this orbital, In this case, it is an orbital and it's also a subshell. If we're going to start putting electrons into this orbital, we have to fill everything that's a lower energy, because electrons are going to go into the lowest energy orbital first. Where do we start? 1s2. Then where do we go? 2s2. Then where do we go? 2p, and it's no longer 2. The 2p subshell can hold 6 electrons. Okay, then where do we go? 3s, and how many electrons does that hold? 2, and then where do we go? 3p, and that holds how many? It's a p subshell, so it holds 6 electrons. And now we have accounted for 2, 4, 10, 12, 18, 20 electrons. Look at the number in the top right-hand corner of calcium. Is it 20?
Yes.
It is. Okay, so it makes sense position-wise that it should end in 4s2, and we've accounted for all of the electrons. We're pretty confident that that is the electron configuration. That's not the electron configuration it says on your periodic table, right? On your periodic table, it says, is it xenon? Argon. Oh man. It's argon, and then it's krypton right beneath it, and then finally xenon. Man, I got excited. Okay, it says argon. What would the electron configuration of argon be? It would end in what? 3p6. And if you're going to fill this one, you have to fill everything that's a lower energy. So argon's electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. So we can put argon in brackets and put all of that underneath, or replace all of this with argon in brackets. The electron configuration for argon plus 4s2. And there's actually some benefit to doing that, but let's keep going. All right, sulfur. Sulfur is right here, correct?
Yeah.
So according to what I just told you, sulfur's electron configuration should end in what? 3p4, because here's 3p1, 3p2, 3p3, and 3p4. All right? And if we're going to start putting electrons into 3p, we need to fill every orbital that's a lower energy level. Where do we start? At 1s. And 1s holds how many electrons? 2. And then where do we go? 2s. And 2s holds how many electrons? 2. And then where do we go? 2p. And 2p holds how many electrons? 6. And then where do we go? 3s. And how many electrons does 3s hold? 2. And so now we have accounted for 2, 4, 10, 12, 16 total electrons, right? Is the number in the top right of sulfur 16? It is. So we've accounted for all of our electrons, and it ended in the right number. All is well, right? But we're not done now. We need to do iodine. And iodine's going to be fun because iodine is right here. Right? So according to our rule, where should iodine end? 5p5. 5p5. And if we're going to start putting electrons into our 5p subshell, what do we have to do? We've got to fill everything that is a lower energy level first. Where do we start? 1s. And how many electrons fit in the 1s subshell? 2. Then where do we go? 2s. And how many electrons fit in the 2s subshell? Still 2, as it has been in our 3 previous problems. Then where do we go? 2p. And how many electrons fit in our 2p subshell? 6. And then where do we go? 3s. And how many electrons fit in our 3s subshell? 2. And then where do we go? 3p. And how many electrons fit in our 3p subshell? 6. And then where do we go? 4s. And how many electrons fit in our 4s subshell? 2. And then where do we go? 3d, right? Because reading left to right, right after 4s comes 3d. Does it frustrate you that this is the third energy level, but it's higher than 4s? It doesn't? That's fine. It frustrates me a little bit, but that's just the way it is. These d orbitals are huge. And so even though it is a lower energy level, it's a higher, even though it's a lower energy number, it's a higher overall energy than the 4s orbitals. So then we go to 3d, and how many electrons fit in a d subshell?
6.
10.
Okay, sorry.
Well, I'm going to need more space. And then where do we go? 4p, and how many electrons fit in a p subshell? 6. And now where do we go? 5s, reading left to right, top to bottom. 5s comes next. And how many electrons fit in a s subshell?
2.
2. And then what comes next?
4d.
4d. And how many electrons fit in a d subshell? 10. And then finally we get to 5p, and we know it was going to end in 5p5. And now let's check the total number of electrons. You ready? We've got 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 53. Is the number in the top right of iodine 53? It sure is. All is right with the world, right? 2 ways to check our electron configurations. Is it in the right position? Have we accounted for all of the electrons? And the answer to both of those questions is yes for iodine. Now, how could we shorten the electron configuration for iodine? If we don't want to write out all of this, how could we shorten it?
You could do KR.
Yeah, so we can go to everything up until this fully filled P subshell. So we could do krypton, and that would account for all of this, because the electron configuration for krypton, if krypton is in the 4p6 position, you better have filled every lower energy subshell first. Right? So we could do krypton, then 5s2, 4d10, 5p5. Is that the electron configuration given to you? Does it fit all that in? It's a lot to try to squeeze into that little box. Oh, but it's all there. Ooh, they put it in a different order. They did the D first. Very interesting. All right. Any questions? Okay. All right, so now we need to start saying, okay, well, so what? So what? What can we actually do with this? So last week I told you something you need to keep in mind is that every atom wants a particular electron configuration. And what is that?
To have a full P.
To have a fully filled P subshell as the highest energy. Okay? That's what every one of them wants, except with 2 exceptions. Hydrogen and helium. Hydrogen and helium just want a fully filled 1s. Okay? All of our other atoms want a fully filled P as the highest energy level. Gets a little bit complicated when you get into some of the higher energy, but again, there are some more exceptions, but that's pretty much what these atoms want. Yeah, Joe?
So if it has 3 in the P, okay, never mind. I already just figured it out.
Okay. So let's look at carbon. Does carbon have 6 electrons in this 2p subshell? No, it does not, but that's what it wants. Okay? How does it get to there? It needs 4 more electrons, right? Now I will tell you it is very difficult to try to get 4 electrons. So we'll see this when we talk about bonding in January, that what it actually does is it forms 4 sharing relationships with other things, where it will share electrons to get to that fully filled P subshell. It won't completely take them away, it'll share them. We'll talk about how that works again in January. Okay? So, is this going to tend to give away electrons? No. Okay? Which means that it is not what? It's not a metal. Okay? So this would be a nonmetal by our definition, and we also define nonmetals as elements that have their highest electrons in a 2p or in a p subshell. All right, in a p orbital. So carbon is a nonmetal. Let's look at calcium. So here's calcium. Right now, does it have a fully filled p subshell as its highest energy?
No.
No, it does not. How could it get there?
Losing 2 electrons.
It either needs to lose these 2, or it would need to gain all of the 3d and then all of the 4p. Okay? It's going to be a lot easier to lose 2 than it would be to gain, what would that be, 10, 16 electrons? Okay? So calcium's going to tend to lose these 2. If it loses these 2, now it has a fully filled p subshell as its highest energy level. Now are you seeing the value to replacing some of these with these brackets? Because then it shows us how quickly can we go back to that. So if you just did argon plus the 4s2, if if it lost those 4s2, it'd have the same electron configuration as argon. And that's what it wants. That's what every atom wants. So calcium's going to tend to give away 2 electrons. What do we call elements that tend to donate electrons and take on a positive charge? Joe. Metals. So is calcium a metal? You bet it is. And you would predict that because it's a metal and because of some other ways we define a metal, that it's probably going to be a good conductor of electricity. It's probably going to be a good conductor of heat. And it is. It is, which is one of the things that makes calcium so wonderful in cell signaling. But anyways, that's a conversation for another class. All right? So what I want you to do is this. I want you to work with those around you, and I want you to tell me and tell us if sulfur and iodine are metals or nonmetals and why using their electron configuration. Yeah, Tom.
No. What is something that already has the fully filled?
What is it called?
Because metals lose electrons.
Well, that's why we said nonmetals, they tend to take on electrons, but they don't always. So all of these, they already have a fully filled p subshell as their highest energy level. They are all nonmetals.
Okay.
But they don't take on electrons to get there because they're already there, and that's why we said nonmetals tend to take on electrons to form negatively charged ions. But these don't. They're already there. They already have what they want. But we'll get there in just a moment. All right? So I want you to, working with those around you, I want you to come up with a type of element for these. Are they metals? Are they nonmetals? And why, according to the electron configuration. 90 seconds. Starting now.
Okay.
It's raining again. We actually got some snow this morning. It didn't stick, but all right. Sulfur, metal or non-metal? Non-metal. Why? It can get to a fully filled p subshell by gaining 2 electrons. That's very doable. And so that's what nonmetals tend to do, is they gain electrons, become anions. Plus they tend to have their highest energy electrons in what type of orbital? A p orbital. So look at this. Sulfur, how many electrons does sulfur want? 2. How many electrons does calcium want to get rid of? 2. There might be something to accomplish between these two elements. Store that up and think about that for the next, 5 weeks. And we'll see that happening in January. All right, what about iodine? Metal or non-metal? Non-metal, because all it has to do to fill its p orbital is to do what? Or to p subshell, is to gain 1 electron. And things that tend to gain electrons and become anions are non-metals. Okay? Pretty neat, right? So we can now use our electron configurations to make predictions about how these elements are going to behave. Okay? All right. So now let's get into lesson 9. This was all review of lesson 8, maybe taking it to the next step. And now this is lesson 9. How is the periodic table organized? How is the periodic table organized? Okay, first point that we need to make is you need to remember something we've mentioned a couple of times now, that the periodic table is organized or arranged to accommodate the different subshells. Right? There are 10 elements in a block where your D subshell is. Right? Sorry, you probably can't think and write at the same time. But we've seen this first point already, right? That the periodic table is arranged to accommodate these subshells. That's why it's not just one big rectangle, right? To where that middle section is down lower than the left and the right section, and why we have that portion that's just off on its own over on the bottom right. You also need to remember that the subshells are made up of the different orbital types. So our p subshell has what type of orbitals? Our p subshell has what type of orbitals? P orbitals, yes. And our D subshell has what type of orbitals? D orbitals. And our S subshell has what type of orbital, since there's only one? S orbital. Yeah, S orbital. And our F subshell has what type of orbitals? F orbitals. Gosh, it's just beautiful. And it's really cool if you see how these things are shaped. So an S orbital, this is bonus knowledge, but an S orbital is just shaped as a sphere. A p orbital is shaped like a cartoon candy piece. Okay? With kind of two pieces here and then attached in the middle. A d orbital is shaped as 2 p orbitals put together. And then an F orbital is shaped as 2 d orbitals put together, stacked on top of each other. It's kind of cool. Kind of cool. So remember that in some of these subshells, there are more than one orbital. For instance, the p subshell has how many orbitals? Each p subshell has how many orbitals?
3.
It better be 3, right? Because each orbital holds how many electrons? 2, and so if we can hold 6, it's going to take 3 orbitals to hold 6 electrons. So, you brought this up earlier, Josh. The 2p subshell is actually made up of 3 orbitals. The 2px, the 2py, and the 2pz. The 3d subshell is made up of how many orbitals? 5. And I don't remember the letters that they use. I don't think your textbook gives it to you. But I think it's X, Y, Z, and then J and K. And why, I think, why is it that way? I don't know that it is. Why do I think it's that way? I don't know the answer to that question either. Okay? But we can name these different orbitals that make up these subshells. But all three orbitals that make up the p subshell are the same energy level. All 5 orbitals that make up the d subshell are the same energy level. And all 7 orbitals that make up an f subshell are the same energy level. And so we have a rule that says you have to fill lower energy orbitals first before you can fill a higher energy orbital. We have another rule that says electrons want to remain unpaired as long as possible. So if you were to actually go and see where these 2 electrons were, there would be 1 in 2px and there would be 1 in 2py. They wouldn't both go into 2px. Okay? And if we go here where we've got 3p4, 1 would be in 3px, 1 would be in 3py, 1 would be in 3pz. Now we've put at least 1 electron in each, then we'd go back and we could put another one here. So 2 of them would be in 3px, 1 would be in 3py, 1 would be in 3pz. Make sense? It's awesome, right? You love it. You couldn't imagine living life without this knowledge now. Right? It's like I don't even know how I got to this point in my life not knowing this. But now that I know it, I know there's no way I could possibly live without this knowledge. So I'm going to keep feeding it, knowing that knowledge has a half-life. I'm going to keep feeding it so I don't forget it. It's like once you start thinking about breathing, you can't stop, right? It's like your body will do it without you thinking about it, but once you start thinking about it, like you can't stop until you start thinking about something else. Is that your experience? Have you ever started thinking about breathing right when you're trying to go to sleep, and then you're like, now I can't sleep because I'm afraid I'm going to stop breathing? No? This never happened to you? Oh, it's totally happened to me so many times. All right. So this is one way the periodic table is organized. It's also organized around horizontal rows. It's organized around horizontal rows, and we call these periods, which is where we get the name periodic table. It's arranged using, again, horizontal rows that are called periods. It's also arranged using vertical columns that are called groups. Again, it's also arranged using vertical columns called groups. So it's arranged using horizontal rows called periods, arranged using vertical columns called groups. Every element in the same group has its highest energy electron in the same type of orbital. Do you agree? Every element in the same group has its highest energy electron in the same type of orbital. I mean, it really doesn't matter whether or not you agree because it's true. Nobody says you have to believe it just because it's true, right? You can be a crazy person. Like the guy that built a rocket so he could go up and prove that the world was flat. And then his rocket blew up and he died. It's just sad. I'm sorry if you believe the world is flat. It's not true. All right. So let's do this for just a moment. Humor me. Look at your periodic table where iodine is, in that 5p5 position. Right above it should be bromine. Yes? And what is bromine's electron configuration end in? Does it end in 4p5? Because it should. Right above bromine is chlorine. Right? And chlorine ends in 3p5. And right above chlorine is fluorine, and fluorine ends in 2p5. So what do those all have in common?
They end in P. Yeah, they do.
They all end in p5, right? They all, I mean, their names, they all end in E. But their electron configurations all end in p5. Meaning they all need what? They all want what?
A full P.
They all want a fully filled P subshell as their highest energy level. And they all are going to accomplish it the exact same way. And how's that? By taking one electron. And man, are they hungry for electrons. These elements in that group, they are very, very hungry electrons. They behave very, very actively to get that electron. They all want the same thing, one more electron. And they all behave the same way. So they will all behave the same way chemically. Basically, every element in the same column, in the same group, will behave the same chemically because they all want the same thing. They all want the same thing. So they're all going to behave the same chemically. That's pretty cool, right? And we can predict that now because we know electron configurations. We know what they want, we know what they have, and so we know what they're going to do to get what they want. If only people were this predictable, right? Some people are that predictable. I know what you have, and I know what you want, so I know what you're going to do to get what you want. Children are that predictable, right? Children. We went camping Friday night for a birthday party my son got invited to. And it was a 9-year-old birthday party. All of the boys there were 9 except for my son. And they decided they were going to go camping for this birthday party. It's a wonderful idea unless your birthday's in December. Then it's a horrible idea. Most years, this year included. Last year, December was very mild. It was actually pretty warm. But it's not normal, right? Normally, December is not very pleasant. So we spent a lot of time in the bus converted into an RV. I mean, the boys were running around like maniacs, but the adults spent a lot of time in there because it was cold. And so whenever the boys would come in, they would join with what we were doing. And what do you do when you're just sitting in a bus? I mean, you eat chips, of course, right? So we're all just sitting around eating chips. And so every time the boys come in, that's what they do. They just eat more chips. And my son, who's 5, wants to keep up with the boys that are 9 and wants to eat as many chips as they do, right? Which works okay for the 9-year-olds, does not work okay for a 5-year-old with a 5-year-old sized stomach trying to keep up with 9-year-old boys. And so my son woke up Saturday morning feeling a little bit sick. The other boys felt fine. They keep eating. He keeps eating to keep up with them. And then by the time he gets into a moving vehicle, it wasn't pretty. But it was awesome. It was awesome. You can use your imagination to figure out what happened. All right, so how is the periodic table organized? Let's answer this question. How is the periodic table organized? There's several ways we can answer this. I think the best way to answer this is like this. It's organized so that it's as IT''S, I think. Yeah. So what do you call that? A conjunction? Is that a conjunction? A contraction. Contraction. It is. It's organized. It could be. Yeah. So it's organized so that every element in a column, so it's organized so that every element in a column behaves the same. it's organized so that every element in a column behaves the same. Bless you. Which is really quite beautiful, because the periodic table was put together before we had discovered all of the elements. And so people were able to predict how an element nobody had ever seen before would behave because of what its electron configuration would be. And then somebody finds the element, and lo and behold, how does it behave? Exactly the way you predicted it would, which actually helped them to find it in the first place. And then I don't know if you knew this or not, but some of the elements on the periodic table, they're man-made. They don't actually exist in nature, but they are man-made. And so you have one called BK, berkelium, and not right next to it, right next to it, CF, californium. Both of those were made in a lab where? University of California at Berkeley. Californium and berkelium.
American.
Oh boy.
Einstein.
Einsteinium. So some of these are not naturally occurring, but they were made in a lab.
And most of the radioactive ones are man-made.
Yeah, I mean, so almost all of the man-made ones are incredibly unstable. So as soon as you make them, they fall apart. You make them and then they fall apart. And you're like, no wonder they don't occur in nature, right? Because if they did, they would just fall apart.
Sounds like kids.
Yeah, when you make them, they fall apart. I like that. That's a good analogy. You know what, I was thinking about another analogy, and I want to share it with you. It has nothing to do with this class, but it was a good analogy. See, some people they're not a great fit for like whatever the position is, but they're a really good like worker, a really good employee. So you fit them into that position, even though it's not a great fit. I don't know if you've experienced all that much in your life so far, but it happens all the time, right? It's like they're just really good at what they do, so they may not be a good fit, so you do what's called shoehorning them in. And that's an analogy that already exists. Like if you try to wear a pair of shoes that is really tight, you use a shoehorn to actually get the pair of shoes on. It almost looks like a crowbar, but you slide it down the back of your leg and you stretch that shoe over the foot. Okay, it's called a shoehorn. Anyways, so that's an analogy. I didn't make that up. That's a good one. You shoehorn something in. It means to get something in there that doesn't exactly fit. So then I was thinking about this, and I'm like, I totally understand. Because sometimes the foot will fit in the shoe, right? Something's got to fill that shoe. Otherwise, the shoe is lonely, right? Just in the same way, somebody's got to do that job. And so you could either get somebody that fits well, right? That shoe goes right on, but it might be an ugly foot, right? It's a good fit, but it's an ugly foot. Or what you can do is you can take a great looking foot and shoehorn it into the shoe, right? The shoe's got to be filled. It's okay if the foot doesn't fit in there exactly. We can shoehorn it in if it's a good looking foot, right? I don't know why I was thinking about this, but I'm like, man, this is a really good analogy. So I thought I'd share it with you. Yeah, Tom.
It also works in that you could slightly ruin the foot by shoving it into a
You could. Yeah, so I don't know if you knew this or not, but the original story of Cinderella, it's pretty dark. And so the stepsisters, they try to shoehorn their foot in, it doesn't fit, so they saw pieces of their foot off to get it to fit into the glass slipper.
But then they can just see that it's all bloody, and they're like,
Right. Yeah. So that the foot got ruined, right? So if the fit isn't anywhere close, I understand. This was you, right? You shouldn't try to force even if it's the best looking foot ever. If it doesn't even come close to fitting in that shoe, you can't even shoehorn it in, right? If you've got to saw pieces of the foot off to get it in, right? That's a different thing altogether. But if you can shoehorn it in, so it doesn't fit exactly, but it's okay, and it's not going to ruin the shoe, right? The shoe's got to exist, right? You can't just get rid of the shoe, and you don't want to ruin a good-looking foot,
And
right?
also, Cinderella slippers are originally made out of fur. but the word for fur looked a lot like the word for, I think it was
Glass.
in French or something. So then they got it mixed up. So now it's glass.
Interesting. How would you wear a shoe made of fur to a ball?
Cold.
Yeah, I guess. Yeah, if it is cold. But I mean, if it's cold, why not stick your really nice shoes inside of like some Ugg boots? Show up, take those Ugg boots off, and now you got your really nice shoes. Anyways, that's just a thought. All right, so what are the names for the various groups? What are the names for the various groups? Because now we've got a dynamic where we know all of these elements in the same group behave the same way. Let's start naming some of them. Right? Seems reasonable. The very first column, so all the way on the left side of your periodic table, those are the alkali metals. The alkali metals. Lithium, sodium, potassium, rubidium, cesium, and francium. Okay, the alkali metals. Not looking at your periodic table, don't look. Don't look. Don't look. What is their electron configuration going to end in? S1. So what are all of them, bless you, what are all of them going to want to do? Get rid of that electron. These are going to tend to lose an electron. They're all going to behave the same way because they all have to do the same thing to get what they want. Right? You know what they have. They have a lone electron in an S subshell. You know what they want. A fully filled P subshell is their highest energy level. They all are going to do the same thing to get what they want. Lose that lone S electron.
So does that mean that most metals end up negatively charged?
Yes.
And non-metals end up positive?
Yep, absolutely. It does mean that. Yeah, Tom.
So why does it say that they tend to lose an electron? Like, why would they not lose an electron?
I mean, if they're not particularly reactive. So I mean, they're all going to basically do that, but sometimes they'll form like a metal with just themselves, like sodium metal, where you have a whole bunch of sodium ions all bound together, and so an individual atom, you don't have access to an individual atom. If you have access to an individual atom, it's going to lose an electron. But if you don't have access to an individual atom, it's not going to, so that's why we use the language tend to. That's a good question. So choose anything in there. Any of those alkali metals. Don't notice hydrogen is colored differently. It's not actually an alkali metal, even though it will behave similar. Hydrogen is a non-metal. It just defies all the rules. I mean, hydrogen's wonderful. So let's choose one there. Let's call it sodium. All right. So sodium's going to lose an electron. Yes, to get what it wants. Iodine is going to gain an electron to get what it wants. Match made in heaven? Maybe. Save that for January. All right, second column. These are the alkaline earth metals. Second column is the alkaline earth metals. Like calcium and others. Second column is the alkaline earth metals. Not looking at your periodic table, what is their electron configuration end in? S2. 2s2, 3s2, 4s2, 5s2, 6s2, or 7s2. And what are they going to do? They're going to lose 2 electrons. Tend to lose 2 electrons. And again, same reason why we use tend to for the first one. If you have an individual atom, it's going to lose 2 electrons. If you have a whole bunch of them stuck together forming a complex metal, you don't have access to a single piece, not much you can do. Which is kind of fun when you're doing a lab. Sometimes you have to shave pieces of the metal off so you can get access to a single atom to get it to behave the way it ought to. I mean, it's really the way it wants to. It's probably not the way it ought to. All right? Now you have to go all the way over to the second to last column. You're like, why don't any of the other ones have names? I don't know. But if you go all the way over to the second to last column, we call these the halogens. We've already talked about these. Fluorine, chlorine, bromine, iodine or iodine, if you want to keep that "een" sound. Iodine. My 3-year-old watches Peppa Pig, and so she pronounces things in British now. She says tomatoes and potatoes and zebras, and you can't convince her that that's not how you pronounce it, because that's the way Peppa Pig pronounces it. Okay, second to last column, these are the halogens, and what are they going to do? They're going to gain an electron. And tend to gain, this is for the same reason, although instead of a whole bunch of them sticking together, you just get two that'll stick together sometimes. And then finally, the very last column, these are the noble gases. They already have a filled p subshell. They already have what every atom wants. And that's why we call them the noble gases. They already have what every atom wants. They don't want to play with anyone. They're noble. The nobility. They already have what every atom wants, and so they are very, very unreactive. Unless, of course, you light them up with electricity, and then they'll emit light, which is why they're great to build light bulbs out of. Neon lights, argon lights, even helium lights. All right? How should we answer this question? Real quickly, we're a minute over, I'm sorry. What are the names of the various groups? C-list. S-E-E space L-I-S-T. All right? And that's it. That's all I got for you. Have a wonderful week. I will see you next week. Ladies, I need to give you your... Are you done writing this down? Everybody done? Okay. Let's stop the recording.